So my name is Krisztian Benyo. I'm a technical business developer and quantum solutions expert at Pasqal, a France-headquartered global quantum computing company. And for the next 2 weeks, I'm going to be hosting this or giving this workshop series to introduce you to quantum computing through the eyes of a neutral atoms type quantum computing device. For this, let me share my screen. I've prepared quick support to guide you through the different elements. If you could just briefly confirm that you can see my screen correctly.
Yes, we can see your screen. Thank you.
Perfect. For today's session, we have planned a general introduction and a quick overview on what quantum computing is and is not. And we are going to start our deep dive into neutral atoms type quantum computers in particular. For today's agenda, we have three main elements. The first and really the introductory part is going to be about quantum information theory. So really to introduce the main concepts of how information is different, how information works on a quantum level, what it means for a quantum computer to carry out these computational tasks. From then on, from this purely theoretical concept, we are going to move to, I would say, the practice in a sense, and we will going to discuss how quantum computers are being built currently, what kind of technologies exist there out there, and we are going to take a closer look at neutral atoms or cold atoms type quantum machines. And finally, for the end of today's session, we are going to discuss in general the role of a quantum computer as of today and in the coming years. And we will put a huge emphasis on how to evaluate the performance of these quantum computers. So what are the different performance metrics there are out there and how you can make the most use out of it. So let's start by introducing quantum information theory. For that, the first and foremost thing that everyone needs to keep in mind is the fact that quantum computers work inherently differently from classical computers. And this starts by the unit of information itself. So classically, when you're dealing with your current computer, everything boils down to handling bits, so zeros or ones, presence of or absence of an electric signal in a transistor on which everything is built up with the current classical, conventional computational technologies. So if you want a very simple real-world analogy is how normal traditional doors work. So 0 can be interpreted as a closed door and 1 can be interpreted as an open door. So for this conventional door, these are the two possible states, the two possible positions it can find itself. When we start discussing about quantum computers, so the unit of information in this case is a quantum bit or a qubit for short, and it becomes inherently more complex. So it's not just complex from a mathematical perspective, but it is also fundamentally different to how this classical counterpart works. To go back to the door analogy to illustrate the complexity, instead of a conventional door for a quantum computer, you would need to imagine a revolving door, so a door that turns around this axle, which can still have a 0 position when it's fully closed. It can still have a 1 position, so to speak, when it's fully open, but it can have a infinite amount of intermediate positions where it is partially open. There is a small gap or a larger gap. This is just to illustrate the initial complexity, but the story doesn't end here. When we talk about quantum bits, we have to mention multiple physical phenomena that govern this complexity of the unit of information. So the two main concepts that dictate this are superposition. So the fact that information itself can somehow be in between the 0 and the 1, so these main reference states. So this can be interpreted as being in the same time 0 and 1 with some manner of probability, or really can be interpreted in something staying in between these two reference states from a continuous perspective. The second one, something inherently present for quantum systems, is entanglement. A notion that can be observed once you have multiple quantum bits, multiple units of information at your disposal, which in a sense illustrates that information can become connected in between these units of information, meaning that if you were to modify one of these informations, that would change the state on the other counterpart as well. But more on that a little bit later. This is just to give you the whole concept of and being fundamentally different for a quantum bit from classical bits. But how to build up this difference? So from a mathematical perspective, we have to start really on a foundational level. So for this, I'm going to introduce a set of axioms or postulates, as they call in the quantum mechanical world. So these postulates are key facts, fundamental laws that every system in this definition setting has to abide. And they are opposed to what we call theorems in mathematics that require proofs, that require justification for their pertinence. So for quantum mechanics, there is a set of postulates that have been defined a couple decades ago already. So the theoretical foundation is well laid out nowadays. There are in total 6 axioms for quantum mechanics, of which the first 3 axioms or the first 3 postulates will be of interest to us. So here I stated in a little bit more vulgarized fashion what these postulates are about, and then we are going to go through these 3 in more detail to explain how quantum bits work, how they can evolve, and how we can access the information on these quantum bits in a sense. So indeed, the first postulate revolves around the fact that it defines what a quantum state is. So it defines the mathematical nature of what a quantum bit is. The second postulate defines how quantum information can evolve from a mathematical perspective. What does it mean to do an elementary operation, in a sense, on your quantum information? And the third axiom defines what we call measurement, so the observation, recovering information from the quantum world to the classical world. As I mentioned, there are in total 6 axioms that lay down the fundamental laws of how quantum mechanics works from a really theoretical perspective, a theoretical point of view. So here I stated the more precise, so the physics or physical and mathematical statement of each postulate. Nevertheless, we are going to focus on the simplified versions of them, again, for the first 3 postulates to define what quantum information is, how it can evolve, and how we can access this quantum information. These are the first 3 postulates. Starting with the first one, so defining what quantum information is, I started the course with an analogy with by using the doors, so a door being open, closed, or revolving around itself, but the actual vision can be presented slightly differently to illustrate the actual complexity of what is a quantum bit. For this, we have to use a different kind of representation. For this analogy, I'm going to talk about the globe, so the surface of the Earth, as a means to encode information in a sense. So if we were to consider that the surface of the Earth, a fictional Earth in this case, would be your quantum information or your information in general, if you were to look at this information from a classical computer's perspective, what you would see is the North Pole and the South Pole, so 0 and 1, and everything else would be lost to you. However, if you were to look at this same information, so again, the surface of the Earth from a quantum computer's eyes, from a quantum computer's perspective, suddenly the whole surface becomes a potential quantum information. Moreover, how you would describe your position on the surface of the Earth. So using coordinates, GPS coordinates, for instance, you can use, in a sense, the same formalism to describe quantum information. The key message here is that quantum information has 2 degrees of freedom. So the 2 coordinates, the longitudinal and lateral coordinates you would use to describe your position. The 2 main components, the 2 degrees of freedom of quantum information that come out whenever you are actually manipulating, whenever you are actually describing a quantum system. From a more mathematical perspective, this representation is called the Bloch sphere. So it is actually a sphere. We are mostly dealing with the surface of the sphere for full quantum information. Nevertheless, the inside of the sphere can also be considered as a partial quantum information in a sense. As I mentioned, how you would describe your position on this sphere would be by coordinates, by 2 coordinates, by 2 degrees of freedom that have a physical meaning for the quantum information as well. The longitudinal coordinate would correspond to what we call the phase parameter, and the lateral, so the vertical coordinate, would correspond to the amplitude parameter. This mathematical representation of using a sphere, it was introduced by the German mathematician Emanuel Bloch back in the 30s, if I'm not mistaken. And this is based on a simple mathematical observation that the sphere or the surface of the sphere can inherently be connected to what we call the complex plane, in a sense, or the complex projective plane, to be more exact. The reason for this is that when you were to describe the quantum information, so on a single quantum bit, how information looks like, from a purely mathematical perspective, what you would get is this vector using 2 reference states and 2 degrees of freedom. So this is a purely complex vector in a sense, and you use geometrical transposition, geometrical equivalence to bring a complex 2-dimensional plane back onto the sphere, so to speak. So there is a lot of mathematical considerations that go into this very simple vision of considering the surface of the Earth as a potential quantum information. But for us, what's important is that for each quantum bit, you can really think of the information, to visualize the information as a surface of the sphere, a position on the surface of the sphere, on the surface of the globe, if you wish. Moving on to the second axiom, now that we have an initial inkling of how quantum information itself works, the next thing we need to understand is how information can evolve, how we can actually manipulate information. And the second axiom actually defines your permissible operations in a sense. This is what we call unitary evolutions. So here we are entering into the theory of the territory. Here we are entering into the territory of advanced linear algebra. So using operators to describe the evolution of these complex vectors in a sense. So these evolutions need to be from what we call, mathematically speaking, unitary. So here you can see the mathematical definition of what a unitary evolution actually means. So it is inherently connected to a reversible operation in a sense, but it is not equivalent. So the two notions are not the same. These unitary evolutions can take very, very different shapes, very different forms, based on what you choose to manipulate specifically. For this reason, when we talk about quantum computers or quantum computing in general, we can distinguish two types of quantum computers based on how it is approaching computation from a really, really abstract point of view. So on the left-hand side, what you can see is what we call a digital or quantum logic gate-based quantum computer paradigm. So a digital or quantum logic gate-based quantum computer is focusing on local interactions and local evolutions on an individual or a 2-qubit level. So we are really focusing on individual units of information and making evolutions, making manipulations through a predefined set of what we call unitaries. So basically, we are given an elementary set of operations. These are called quantum logic gates. And we can apply this set of instructions on the individual quantum bits, on the individual units of information. So this is really reminiscent of how your classical computer works on a very, very fundamental level. So everyone has learned it in school that logic gates, so and or not, manipulate information, binary information, so the zeros and ones, on a very, very low level. So in your classical computer, you use these logic gates to carry out repeated operations, which build up step by step the actual instructions you want to carry out for your everyday use. A digital, so quantum logic gate-based quantum computer works in a similar fashion, so focuses on individual local interactions on the single or two quantum bit level by referring to a set of admissible quantum logic gates, so elementary operations. On the other hand, there is another approach that's called an analog quantum computing, which focuses on a more global interaction. So it forgoes this local decomposition and focuses on almost instantaneous, but one-time evolution of the whole system. So it takes into account all your quantum bits, all your quantum informations as a many-body system, as a many-entity system, and makes the evolution over the course of time in a much more complex way. So this is something that has actually existed with classical computers as well. So in a classical sense, back in the 70s, there was an analog way to do computing. However, it is inherently incompatible with how classical information, so the bits, zeros and ones work. Therefore, it very quickly fell out of fashion, and the digital, so the logic gate-based approach became dominant, and this is still what we are using. For a quantum system, however, since information itself is continuous by nature, so it's not something discrete, having this elementary decomposition can be an advantage and a drawback as well. Therefore, the analog approach has its actual relevance. So putting this into a different perspective, the digital quantum logic gate-based approach focuses on reproducing in a similar logic to what you would have in a classical computer, a local series of interactions to construct what we call quantum circuits. So this is still predominant in the quantum computing world as well for now. However, it is not the only way to go about quantum computing. On the other hand, the analog approach that has much more relevance for quantum computers due to the fact that quantum information itself is inherently something much more complex, continuous in nature. Therefore, the analog way to carry out the computation, so doing a continuous in time evolution, hence the name, is much more relevant, much more pertinent, and can give rise to very, very interesting applications. We will see a couple of these examples throughout the various sessions of the course. For now, I just wanted to introduce the two concepts in order to have a perspective of where we stand in terms of quantum computing from a theoretical level. Taking a closer look at how quantum computing itself works in these two different paradigms, for the analog approach, so for a continuous in time evolution, what we are in need is what we call a Hamiltonian. So we need to define this mathematical operator that's going to dictate how your quantum information will evolve on the whole set of quantum bits at the same time. So here we are not limited to individual interactions or a fundamental set of interactions. We are really focusing on the whole picture. Therefore, depending on the type of system you are dealing with, you have different ways to represent this Hamiltonian, this global interaction, but in practice, the form can be quite free, so it's not limited to specific types of interactions. So this is typically something that you find in quantum simulation type experiments. So describing how quantum many-body system works on an atomic or electronic level. So this is really on the physical layer, on the very, very low level, how quantum information can be manipulated. This is always the foundation. On the other hand, from the digital quantum logic gate-based side, as I mentioned, you are in need of a fundamental tool set, so an elementary toolbox, these quantum logic gates, to be able to describe how you can manipulate, how you can evolve quantum information. So here I've chosen again the mathematical representation, which is done through matrices for the operators. We can define specific types of quantum logic gates. So since quantum information is inherently more complex than classical information, the types of logic gates that are permissible are much more varied. In a typical fashion, we tend to talk about rotational gates, which is a specific subset that can form a unitary basis. So part of this fundamental toolset, you probably have seen, for instance, the Hadamard gate, but there is also a lot of other types of quantum logic gates that can be introduced depending on the basic toolkit you have chosen. So The tricky part here is that from a theoretical point of view, there are many equivalent representations. So here, this form is really one of the most generic representations of how a quantum logic gate looks like. In practice, you are choosing a predefined set of quantum logic gates so that you are able to reproduce any kind of interaction. But the choice of this predefined set of quantum logic gates is dictated by the physical device, so what kind of gates you can practically implement, so moving away from the theory, but it is also dictated by the mathematical constraints that your quantum logic gates in total need to form an actual basis. So you need to be able to reproduce any kind of evolution over the whole system by applying a series of these elementary operations. With that said, one of the main bottlenecks and one of the key principles that people are having a more harder time grasping their heads around is related to the third postulate, so the third axiom of quantum mechanics, which relates to observation, which relates to measurements. So up until now, what I've described with quantum information theory is something that only exists on a quantum mechanical level. So really inside the quantum computer, if you wish, on this very, very, very low level inside the proverbial box. However, we do not live in the quantum mechanical world. So for us, the information that we can actually use and process needs to be recovered from this quantum world in a sense. And to illustrate the conundrum here, back in the 30s, Erwin Schrödinger has introduced a very interesting thought experiment that relates to the fact that how different these two words, so the quantum world, the world of atoms, electrons, and other particles, and our macroscopic world works. So to describe briefly the experiment, you are given a box. Inside this box, you're going to put a fictional cat. Next to this fictional cat, you are going to put a particle, some kind of particle, and with this particle, there is also going to be a detector inside the box that is able to detect the presence of this particle. The detector is then connected to a poison, and with this setup, you are going to close the box and release this particle that you have kept inside it. So two things can happen according to Erwin Schrödinger. So the first thing, the particle bounces around, goes around its merry way, and it gets detected by the detector. If it gets detected by the detector, it will release the poison, which in turn will kill our fictional cat. However, if the particle is not detected by the detector, the poison will not be liberated and the fictional cat will stay alive. So the question he asked to his audience after this experiment is, now that I have released the particle with the closed box still in front of me, how can I say, or what can I say about the cat? Is our fictional cat alive or is our fictional cat dead? He accepted multiple correct replies in a sense, but all these correct replies revolved around the fundamental concept that you don't really know if the fictional cat is alive or dead unless you actually open the box. But as soon as you open the box, you have determined the state of it. So you have lost this uncertainty in a sense. So the first correct reply he accepted was that the fictional cat is at the same time alive and dead, which he used to illustrate what we now call superposition. So the cat is at the same time in the living state of 1 and the dead state of 0. He also accepted the reply that the cat is neither alive nor dead. So it's really in this, so to speak, third state, this uncertain state that we cannot know until we open the box. But what happens once you open the box, you have determined the state. You have determined whether the fictional cat is alive or dead. And afterwards, no matter how much you open and close the box again, the cat will stay alive if it was alive when you opened the box initially, or the fictional cat will stay dead if it died during the initial experiment. This boils down to two key notions regarding measurement. So the measurement in this thought experiment is the fact of opening the box to actually know what's the value, what's the state. So the first key fact is that the information we can actually recover following a quantum computation is always one of the reference states. So what comes out of the quantum computer in a sense is a 0 or a 1. If you're given multiple quantum bits, so you're dealing with larger state, that will be a series of zeros and ones, so a bit string representation. But that's what comes out of a single experiment, a single iteration, a single shot, what we call it. However, that is just a trace, that is just a footprint of the actual quantum information. So you simplified heavily the initial complex information, so this two-dimensional complex vector, into a single footprint, one of the reference vectors. So by recovering the information, by getting a readout, by doing this measurement, you have destroyed part of the complexity of the system. So by opening the box, you have determined whether the fictional cat was alive or dead. Which boils down to the second problematic, is that if you want to know more about the quantum information itself, you need to repeat the actual experiment. And you need to repeat it potentially many, many times. By repeating it, you can get a probabilistic notion of where your quantum information is, in a sense, to some degree. So here, what is represented is the mathematical formulation of how you can determine by discrete probability tools what is part of the quantum information at hand by repeated experiments. But it still does not give you all the complexity of quantum information. So this will come back later when we talk about performance metrics, when we talk about how you would evaluate the performance of a quantum computing algorithm. For now, I will leave it to the fact that considering how many repetitions you need to make, so how precisely you need to recover the quantum information is a key factor in evaluating quantum algorithms, and it is inherently tied to how the system works, so how quantum mechanics itself works. This, however, is a constraint only for measurement-based quantum computers. Sorry. There are other types of quantum computers that deal with this paradigm, this restriction of having limited access to the quantum information for the classical world in very different fashions. However, with this restriction, there is also a flexibility, because measurement, so this observation can take many different forms. So with mathematical tools, you can represent it quite easily. So you are not necessarily limited to reading out the two reference state vectors, 0 and 1. you can construct objects that will read out something entirely different from your quantum system. So this is part of the algorithmic consideration, typically when you develop applications, and it has a lot of interesting consequences that you are not limited to what you get out of the system. You are limited in the shape of the information you can recover, but you are not limited in the nature of the information you can recover. So this gives a lot of flexibility for quantum algorithms in particular. Now, with that said, let's move on to the second part of today's course, which will move further away from the theory and closer to the applications. Our application, in a sense, that the physical realization of how these quantum mechanical principles can be applied in the real world. So up until now, what I've talked about with quantum bits, unitary evolutions, and measurements is really a theoretical concept. So this is how mathematicians and theoretical physicists envisioned quantum computers should look like. But in practice, the real world is typically slightly different from what the theory dictates. Not only there are imperfections, there are a lot of additional constraints to take into consideration. With quantum computers in particular, there are many different physical considerations to take into account for. So the first of these considerations is the nature of the quantum bit. So we know from a theoretical point of view how quantum information looks like, but how you implement it in the real world, you have many different options. So this is unlike classical or conventional computers that all based on transistors, all based on the presence of or absence of electric signals. For quantum computers, you can choose many different types of quantum mechanical entities, so different particles, to build your computational device. So here I've listed, I would say, the 5 main types of technologies that are currently dominating. Sorry, it's not a comprehensive list. I will give a bit more comprehensive overview in a bit. This was just to illustrate that the choice of the physical medium, how you realize quantum information, can have a huge impact, and it is much more diverse than what we have seen so far with classical computers. For today's and for this workshop session, we are going to focus on neutral atoms or cold atoms. So that technology will be highlighted with more details, but there are other types of pertinent and relevant technology, all with their physical advantages and potential drawbacks, and that we are going to discuss when we talk a little bit more about the metrics section of today's talk. But to move ahead, an interesting overview that I like to present a lot is this collection of quantum computing players by technological access. So as you can see in this more detailed panorama, there are 8 different technologies, 9 different technologies, technically, but let's stick with 8 different technologies being distinguished based on the physical medium chosen to carry out, to construct a quantum computer. The first type of quantum computer, in a sense, is what we call an atomic or atom-based quantum computer that has 2 slightly different from a theoretical point of view, slightly different, from a practical point of view, very different types of quantum computers, so trapped ions and cold or neutral atoms, which the second one will be the focus for today. there is a lot more flexibility when you base your unit of information on an electronic state, in a sense. I think that most of you have heard at least about the superconducting type quantum computers, being that this is one of the first type of quantum computers that appeared, historically speaking, and this is one of the more developed technologies, but this is not the only viable option for an electronic type quantum computer. And finally, there are photonic type quantum computers, which base themselves on manipulating light particles, so photons, and their various properties. We are going to discuss a little bit more about the key features of these technologies. For now, I just wanted to illustrate that, yes, theoretically speaking, we understand, we know how quantum information works in practice. So from an engineering perspective, there are a lot of different choices to make to build up your quantum device. And now we are only talking about I would say, the real world implementation of the first axiom. So the first postulate on defining what quantum information is. We haven't even mentioned how the other postulates can be implemented, which gives a lot of other degrees of freedom in defining a quantum computer. What I wanted to highlight is a key notion on top of the physical nature of a quantum bit. So we have seen when we discussed the second postulate, the second axiom on how to make the quantum information evolve, that there are two ways to manipulate quantum information. There was the digital, so quantum logic gate-based evolution of the quantum information, and the analog, so continuous in time evolution. What we can see here in this very schematized or simplified graph is how these two ways of quantum computing are evolving over the course of time. And this schematic representation introduces a few very, very interesting notions that everyone needs to be familiar with. So currently, nowadays, and for the next 1 or 2 years at the very least, we live in what we call the NISQ era. So it's noisy intermediate scale quantum era. This refers to the fact that the physical implementations of quantum computers have still not reached their full potential. They are still noisy in a sense that quantum information has a lot of noise, has a lot of error in it, and it is intermediate scale, meaning that the available quantum informations, the available capacity of information is limited to some extent. This does not mean that quantum computers are not useful nowadays. It just means that there are some particular quirks about the actual physical realization of quantum information theory that you need to account for when you consider any kind of application. This is something that will slowly evolve towards what we call quantum advantage, and then what will evolve into fault-tolerant quantum computing, so FTQC era. So when that will happen exactly, we do not exactly know. There are different predictions. Here, in this timeline, it is predicted for 2028 or even later. Some people think that already next year or the next 2 years, we will reach this regime. It is really, really undecided at this stage. What is important is the notion itself of fault tolerance. So fault tolerance or fault-tolerant quantum computing refers to large scale and almost errorless computation with quantum devices. So there is a very precise definition of what we mean by almost errorless. We won't go into the detail for now. It's not that important for the current talk. I just wanted to mention that these two notions of where quantum computers are now with the NISQ type machines and where quantum computers are headed with the FTQC, so fault-tolerant machines, have been and will be the key driver for the technology, at least from the hardware perspective. On top of it, we add the notion of quantum advantage, which can mean a lot of things for very different people. For industrial players, it has a very specific definition. However, mathematically speaking, or its initial definition is and has always been to be able to solve problems that are infeasible with classical computational means. With this introduction, to illustrate the diversity of quantum computers, now I'm going to focus on a neutral atoms or cold atoms type device in order to give you a more detailed overview of how these type of quantum computers work. So a neutral atoms or cold atoms type quantum computer uses atoms, as the name implies. More specifically, it uses the energy levels of atoms, of specific atoms, to encode information. So for us, a quantum bit, physically speaking, is a specific atom in a specific electric state or a specific excitation state, so to speak, on a specific energy level. How it is carried out? It is carried out by an optical setup. So the devices themselves are optical installations that use various lasers to carry out different components of the computation. Lasers are being used to position, to sort of create, in a sense, the architecture, the layout of it. So to have the atoms at specific spatial positions, lasers are used to move around the atoms if needed. Lasers are used to send information to these atoms, to the whole system, to make it evolve as a whole. So lasers are the main means to physically realize the architecture. Lasers are the main means to carry out the computation. In this sense, so what we have seen from a theoretical point of view, in order to define what a quantum bit or a qubit is, we need to understand a specific set of elementary tools or elementary notions. First of all, we need to identify what are the reference states. So the 0 and 1, which, as I mentioned, correspond to energy levels, specific excited states of an atom. So in the case of Pasqal in particular, we have taken the choice to use a rubidium atom or a specific isotope of rubidium atom. So rubidium atom is a light metal that has a single electron in its very outer electron layer. It has been one of the few atoms that were used with modern optics experiments for the past 2, 3, almost 4 decades now. So since the 80s, to carry out different atomic experiments. They are the foundation of the technology because they are not too heavy, so that gravity would be an issue for manipulation. They are not too light, so that the atomic kernel itself remains sufficiently stable when exposed to laser light. And they don't have too many free electrons, so too many electrons in the outer electron layer, so that the energy states, the types of energy states it can accommodate remain relatively simple compared to other types of atoms. So these three constraints, so having an atom that's not too heavy, not too light, and not too many electrons in the outer electron layer, reduces the choice of atoms to a selected few of them. So typically, for these type of devices, one considers rubidium, strontium, ytterbium, and in some cases even cesium atoms. Rubidium is one of the, so to speak, simpler options and one of the more historic options due to the fact that it's one of the lighter candidates and it only has a single electron in the outer electron layer. We use the ground state as a reference, so the atom in its fundamental ground state as a zero reference state, and the one state refers to a specific hyperexcited state that's called a Rydberg state. So a Rydberg state refers to the fact that certain atoms can reach, given sufficient energy, a very, very high energy state in which the outer electrons can be sent to a very, very high atomic number, so a very, very high orbital. In the case of rubidium atom, this high orbital can reach the 60s to the 70s for the orbital number, which means that it is capable of long-range interactions in a sense. But more on that later. For now, we are using these rubidium atoms and the energy levels of these rubidium atoms. As I mentioned, we are working with an optical setup that uses lasers, not only to trap the atoms, so not only to create these patterns that you can see on the top right, which are actual images taken from inside a neutral atoms type quantum computer. So each lighted dot corresponds to an individual atom inside the setup. For a neutral atom system, this would be, so to speak, the equivalent of a microchip. So these machines are not limited to set fixed architecture, so it's not physically constrained, unlike microchip based, so superconducting or other semiconducting based computers. They are practically being suspended in vacuum. So everything is happening inside what we call a vacuum chamber. We will see the actual visualization in a bit. Each lighted dot is an individual atom that is being trapped by a specific focused laser light. So it is called an optical trap, or an optical tweezer, which is a specific focused laser light that creates an energy well in which if the atom enters, it does not have enough energy to leave it. So it is really a trap in a more conventional sense. How we create these images, so that relates to the measurement in a sense. It is called fluorescence imaging. So we are measuring, we are trying to capture photons emitted by the atoms that is present even in their ground, in their natural state. That's why you see these lighted up dots that really are corresponding to individual atoms. And as I mentioned, these specific atoms, especially in the hyperexcited state, they can be seen as they can interact with each other. This interaction is carried out due to the fact that if you have an atom entering this hyperexcited state, and you would have an atom next to it. So you see the image on the bottom right. The atom has sort of an interaction range. So if two atoms are trying to enter into this hyperexcited state at the same time, one of them would be needed to move into a lower energy state. Both of them cannot accommodate this high energy state, and this is referred to as the Rydberg blockade. And this is the basic principle, the underlying principle behind how neutral atom systems carry out entanglement. So to give you a more visual representation of how these neutral atoms type devices look like, here is a quick illustration of how our machine actually looks like from the inside. So it's really an optical installation that uses lasers guided through an optical table entering inside a vacuum chamber to manipulate individual atoms themselves. So the video will repeat so we can see once again the illustration and the visualization for these machines. So you can see the optical table guiding the laser lights inside this vacuum chamber. So we have entered inside the vacuum chamber where each lighted up dot corresponds to an atom that is receiving information from specific targeted laser lights to carry out various evolutions. And after the evolutions, we use this specific fluorescent imaging camera to recover the information itself. So these were the images you could see in the previous slide. So to give a bit more context on this, on the actual setup, and then we will move on to a couple of the questions, because I've seen that there are a few questions in the chat, so I'm going to address that in a bit. So to give a better understanding of how the setup itself works after this visualization, this is really optical layout and that uses two laser sources in total to carry out different manipulations inside the vacuum chamber. So on the right-hand side, the vacuum chamber or science chamber, as they also call it, is really the heart of a neutral atoms type quantum computer. It is inside this vacuum chamber that we are trapping and manipulating the individual atoms. The trapping happens by specific laser lights that are getting diffracted and modulated to create the energy wells at specific positions. So inside the vacuum chamber, we are targeting specific positions in which we can catch the atoms in a sense. And then we use a second set of laser lights to send energy, to send information to the system to make it evolve. So this evolution can take place in a continuous in time fashion by continuously modulating the laser. And so therefore the energy that is sent to the system. This works initially in an analog, so a continuous in time global manipulation setup, but this manipulation can be carried out with local interactions to create what we call quantum logic gates as well. So in the next session on Wednesday, we will see some practical implementations and some actual initial, I would say, coding type explorations of how you can work with this type of system. What I wanted to mention for now, before moving on to the questions, is that the cycle itself has multiple stages. So for a neutral atom system, there are different phases that each iteration needs to go through. So the first step is to create the traps, so to catch the atoms in specific positions. So the optical trapping itself happens in a random fashion. So you cannot determine which traps can catch atoms. So at this initial stage, the objective is to trap enough atoms for your experiment. So this is illustrated by this first image in which each lighted up dot illustrates a trap that managed to catch an atom. Meanwhile, the highlighted section of it is the part that actually tries to catch atom, where we want to have atoms for the computation. So once you have loaded the register, once you have caught the atoms, the second step is to prepare the computational register to rearrange your atoms by using specific optical tweezers, so fast-moving laser lights that are able to move the atom from one trap to another trap in order to position them in the actual layout you want to have the atoms for the computation. It is after this that the actual quantum processing can happen. So it is at this phase that you are using the second set of laser lights to send energy, to send information to this specific part of the register, to make the system evolve, to carry out the actual computation. And then after the computation, what happens is that certain atoms can become excited. If the atom becomes sufficiently excited, it has enough energy to leave the trap. Therefore, it won't show up on the imaging because it is allowed to escape. By other atoms, if they didn't have enough energy, will stay inside the trap. And it is through this notion of certain atoms leaving the trap by others staying in it that we can carry out measurement in the sense of what we have seen for the third axiom to get an idea of what happened on the quantum level for the quantum system itself. So now, before moving on the third section, I was informed that there are a couple of questions in the chat. Let me see. Yes. So the Rydberg state. So there was a first question about what was the Rydberg state. So let me move back. So a Rydberg state refers to a specific high excitation or hyper-excited state that is typically manifested by having your outer electron layer, so one of your free electrons, in a very, very high orbital number. So I mentioned for the rubidium atom, it is typically between the 60th and 70th orbital. But in general, it really is dependent on the atom itself. So a Rydberg state is a specific hyper-excited state. Then there is a question about what's the optical tweezer itself. An optical tweezer is a specific type of focused laser light that creates this aforementioned energy well. So the optical tweezer is what you can use to have this trap layout to catch an individual atom. However, if you direct the laser light in a good direction, it is a specific laser that can be used to pick up an atom and move it from one trap to the other. So it's really a hyper-focused laser light that's there to pinch, to tweeze. Therefore, hence the name. A single atom and being able to move around the laser itself allows you to move around the atom itself. And it has importance in the register preparation cycle. So when you need to move around your atoms to have them in the specific positions you want to have them. So as I mentioned, to start the computation itself, you need to define traps. You need to define positions of the laser, the focused laser light in which you want to have atoms. And typically, the loading itself, so catching the atoms, is following a Bernoulli type distribution. So it's approximately every second trap that's able to catch an atom. So every 1 out of 2 traps is actually able to catch an atom. Therefore, you need to have enough traps to catch sufficient number of atoms to actually carry out the computation. And then once you have managed to catch the atoms, you need to position them in the specific positions in the computational zone that you want to have the atoms to start the actual computation. So now let us move on to the third part of the discussion, which will start introducing some key notions about the utility, so the usefulness of quantum computers, and how you can actually evaluate the impact, the interest in using these computational devices. The first thing that needs to be mentioned here is the notion of HPC, so high performance computing. Indeed, a quantum computer as it is today and very most likely for the foreseeable future is a computational resource that is there to help out, to complement existing computational resources, typically in an intensive computational environment. So a quantum computer is not like your everyday personal computer. It's not meant to be used for chit chat and or everyday usage, sending emails and whatnot. It's really a dedicated computational resource that can be tasked to solve specific, typically conventionally hard tasks. Therefore, its place, at least in the foreseeable future, is within what we call an HPC, a high-performance computing environment. So a high-performance computing environment is nothing else but a large collection of interconnected computers. Here, we are really talking about computers at the broadest definition possible. And this collection of computers are set up to function as a whole to carry out various different computational tasks that require a large amount of computational power. In a typical setup of a high-performance computing environment or equivalently a supercomputing environment, you have a lot of different CPUs, and a lot of different GPUs interconnected. And there is a strict division set up by software tools that decide when you send a computational task, which computational resources are being used. So conventionally, the high-performance computing centers are already practicing in a smaller scale division of or redistribution of the computational resources in order to allocate the most appropriate computational source for a given task or subtask. With the current and even future infrastructures, we will see the apparition of different types of computers. So quantum computers, for a starter, but I've also mentioned a couple of other emerging technologies, such as neuromorphic computing or simulated annealing, that can all have their place within this high-performance computing environment. The main idea here, once again, is that all these different types of computers are viewed as computational resources that can be utilized to solve specific tasks, and it is up to the software or to the person managing the whole infrastructure to devise the strategy to allocate the best computational resource for a given task. So we already know that CPUs and GPUs have their natural advantages and defaults. But on top of that, with the operation of these new computational resources, new, more advanced scenario can appear in trying to allocate the best computational resource for a specific given subtask. So the idea here is that when a user launches what we call a job, when a user launches an execution of program, computation of something, that task needs to be divided into many different elementary components. And then each component needs to be allocated a specific computational resource. And to make the most use out of this whole infrastructure, you want to allocate all the components to the best computational resource or the most efficient computational resource. So this is how, in principle, it should be working. What we can say is that it is heading this direction in the practice as well. So here I've collected a couple of examples from various high-performance computing centers all over the world. So the first one, since I'm based in Paris, this is the closest to me, is one of the supercomputers here in the Paris region, and that's used by the French Atomic Agency, which is now hosting Pasqal neutral atoms quantum computer on top of the existing CPU and GPU racks, but it is not the only potential example. In general, what we can observe is that these high-performance computing environments are moving to the next stage of evolution, in which they are not only hosting CPUs and GPUs, but they are integrating new emerging technologies, such as quantum computers, but not just quantum computers. And when you consider integrating quantum computers, there are different choices to make. So choices based on the physical architecture. So what type of technology you want to integrate? Typically, you would want to integrate different types of quantum computers, as different quantum computers have different performance metrics. So typically, different technologies can be used to solve specific types of tasks more efficiently, and that can also differ from in between the different quantum computers from a physical perspective, meaning that a neutral atoms type quantum computer might be able to solve more efficiently certain tasks than a supercomputing type device, and vice versa. So the physical difference gives rise to some differences in the applicability. Therefore, the high-performance computing center itself needs to be prepared to accommodate different technologies. On top of that, there is also the intermediate notion, but which is highlighted here with emulators. So a quantum emulator is a classical or conventional computational resource that is parameterized, that is set up to behave like a quantum computer. So it is not a quantum computer, it is a classical computer that tries to behave, tries to emulate how a quantum computer should be working. This is an essential tool, especially in early stage development, in testing methods and testing quantum implementations, in optimizing quantum methods before actually deploying it on the physical quantum computer. So this is an intermediary in between classical computers and quantum computers that are predominantly present in a lot of the current software stacks and hardware architectures due to the fact that classical computational resources are abundant. We have a lot of access to CPUs and GPUs. However, quantum computers are still considered a rare computational resource. With that said, a major question is the actual utility of these devices. So for now, I introduced where, in what sense, quantum computers need to be deployed or are being deployed. now we turn our attention to the question, to what purpose, to what extent we can mobilize quantum computers. When we talk about quantum computing in general, typically people distinguish 3+1, so 4 pillars. So here is a schematic representation of these 4 pillars in which quantum computers can find an edge over classical computational resources. First of all, there are 2 main messages to absolutely keep in mind. The first is that quantum computers are not here to replace classical computers. As I've illustrated in the HPC workflow, they are here to complement, to build upon the existing classical workload in order to bring some improvements. And second of all, quantum computers are still very limited in terms of capability. So these different pillars are more long-term prediction on which types of application, which types of problems we can expect them to have either a short or a long-term impact. So typically, these 3+1 pillars are the simulation. So either quantum simulation, so simulating quantum systems, which is mostly a physics-based experimental toolkit, or simulation on more a conventional setting in a more dynamical setup, so solving differential equations or any other kind of modeling type exercise. Second of all, optimization, which has a huge potential, especially in combinatorial optimization. We are going to focus a lot in upcoming sessions on these types of applications. And thirdly, machine learning. So synergies with machine learning have a lot of untapped potential. It is still very much not yet well understood what can be the actual impact. And we are really talking about the synergy here. So it's not just quantum computers enhancing machine learning or AI processes, but it can go the other way around. Machine learning and AI processes can help enhance and optimize either the physical or the software architecture for a quantum computer. And finally, a very, very long-term, but still important part of the quantum computing landscape is the cryptographic considerations. So digging a little bit more into the detail of each of these axes, you can see different types of problems mentioned more from an industrial perspective. So the key messages here is that most industries will be impacted to some extent because quantum computers as a computational resource are really focusing on the mathematical foundation of the problems and less on the actual applied setting. Therefore, different industries can have similar benefits because they are leveraging the same type of mathematical formulation. The only, I would say, all-encompassing field is really the cryptographic considerations, for which we know that there is a long-standing risk established back in the 90s. So you probably have heard about the Shor's algorithm, created by Peter Shor in 1994. So 30 years ago, from a mathematical point of view, an algorithm has existed that, given a sufficiently powerful quantum computer, is able to carry out integer factoring in polynomial time, so exponentially faster than what is currently known, which therefore is able to break especially the asymmetric RSA encryption, which is currently being used in almost 90% of the cybersecurity infrastructures all around the world. But this So Shor's algorithm is a mathematical algorithm. Its impact can only be seen once you have access to sufficiently powerful quantum computers. By sufficiently powerful, nowadays with the current notions, we know that it's very much beyond fault-tolerant quantum computing. So no one expects to be able to break RSA encryption in a practical manner for the next 5 years. However, the risk from an algorithmic point of view is already there. It is not the only type of problem that can have a lot of impact. And for this, I invite you wholeheartedly to look into the literature of quantum complexity theory. So this is a newly born mathematical field that deals with classifying problems, classifying algorithms in terms of how difficult it is to solve them with classical conventional computational resources. That was the initial field. And with the operation of quantum computers, quantum complexity theory has born that tries to classify problems based on how complicated it would be to be solved by near-term, so noisy intermediate scale quantum computer, or how difficult it would be to solve with a fault-tolerant quantum computing. So because the field itself is quite complex, the notions are a lot more diverse than what we have in a classical scenario. But what's important here is that when people typically speak of easy problems or hard problems, what they have in mind is easy or hard for a classical computer. So from a mathematical point of view, it is important to make the distinction for which device the problem is easy or the problem is hard. And what is known so far in this new field is that what's easy for a classical computer is easy for a quantum computer. There are a lot of different problems that we know are hard for a classical computer, but become easy, relatively easy for a quantum computer. So the prime factorization or integer factorization with Shor's algorithm is just one example, but we can have many other potential candidates for that, from quantum machine learning all the way to optimization. But since the field from a mathematical perspective is quite new, there is still a lot of missing theorems and missing proofs to establish exactly what constitutes easy and what constitutes hard problems for this new emerging technology. The key message here is that when someone talks about easy or hard problems, the first question you should be asking is always easy or hard for what devices, to have the clarification. With that said, the last element I wanted to touch upon for today's session is how you go about evaluating technologies. What are the key performance metrics that you need to keep in mind? So as I mentioned previously, there are different types of physical quantum computers, and each of them have different advantages, not only from the application perspective, but also from the hardware perspective. So here in this table, I have collected most of the metrics that people tend to use all over the world. And then I will build up on this to introduce a couple of more means to evaluate where the physical technology, so where the hardware itself stands, or how close we are to an actual deployment or applicability. When you talk about a quantum computer, the first metric, the first indicator that comes to mind is the number of qubits. So this is something that's the easiest to grasp, but it gets often confused as being the metric, the indicator to compare machines, which is very, very misleading or very dangerous notion. So as you can see, qubit counts or physical qubit counts, I should precise in this case. So the number of physical quantum bits present in a single core quantum computer vary from the tens all the way to the thousands, depending on the technology. Certain technologies have the potential to reach these higher regimes relatively easier, while other technologies seem to have much larger limitations on this. So this is inherently related to the architecture from a theoretical or from a more practical side. In case of the neutral atom systems, since they are using atoms themselves suspended inside a vacuum chamber of atoms, we have a lot. So we have a lot of atoms at our disposal. So the question is only how you can create a sufficiently large optical setup to keep these atoms in place and to be able to interact with this atomic system. Nevertheless, for this reason, neutral atom systems are viewed to have a scaling advantage. They can scale up quite easily compared to other technologies. But as I mentioned, the number of quantum bits, the number of physical quantum bits is not the only metric and should never be viewed as the single indicator to determine how good your quantum computer is. The reason for this is that there is the notion of fidelities or error rates that you commit when you do a quantum operation. So there are different types of metrics that you need to keep in mind with regards to error rates. All of them relate to the fact that information itself can be imperfect depending on the technology. So for instance, for superconducting or spin qubits, you need to manufacture the physical entity that encodes the quantum information. Manufacturing always has imperfections. Other technologies like neutral atoms or trapped ions, they use nature to define the physical quantum bits. So there is no imperfections in that regard. But in the current setup, all quantum computers commit some kind of errors during the manipulation phase. So here we are talking about how you evolve quantum information, how you actually carry out the computation. And carrying out the computation involves having some manner of errors present in the system because it is an artificial process, and artificial processes are never perfect. Even in your classical conventional computer, it commits errors. So albeit the current machine error rate is 10 to the power of minus 16. So it is once every 10 to the power of 16 elementary operation that is incorrect by using the transistors in your classical computer. So it's a very, very low probability, but this also illustrates that errors are being committed by your classical conventional devices already. They are just being corrected and accounted for, and the rate is quite reduced. For quantum computers, they are nowhere near that regime. So you can see here some gate fidelities. Performing a single operation or specific operation on 2 quantum bits produces an error in every 1 in 1,000 or 1 in 10,000, depending on the system, on the best system you are looking at. So we are nowhere near the same regime, but this is just one way to illustrate that any kind of manipulation of the quantum information can lead to some manner of error. So it's a deviation from the expected to what actually happens, which is a cumulative effect from different factors of the physical setup as well as from environmental conditions as well. All this to say that, as I mentioned, the number of physical qubits is just one indicator. It's not the only indicator, because you can have 1,000 physical qubit machine, but if the machine is very, very error prone, then you cannot do any computation on these physical qubits because the noise would be too present in your system. So you need to always consider what are the fidelities, so what are the error rates you commit for individual manipulations, and what are the cumulative error rates for specific types of utilizations of the machine. This is not all still, so there is another important metric here, which is the clock speed. So clock speed refers to the fact of how fast you can carry out the iterations. So we have mentioned from a theoretical point of view that measurement needs to be done to have some idea of what happens inside the quantum system. And depending on your algorithm, you might need to reiterate, to rerun your algorithm many, many times to get sufficient precision with your measurements, with your observations, for a meaningful readout, for a meaningful information that can come out of your quantum computing algorithm. Therefore, knowing how fast your quantum computer can actually compute, can carry out the tasks, is another important metric that has a huge impact on the application side. For this, what you can see is sort of an inverse effect from what we have seen beforehand with the physical constitution of quantum bits. So neutral atoms and to some extent even trapped ions are viewed as some of the slower machines, especially with neutral atoms. I will go back and reason why this is the case. But they are comparatively much slower than electron-based quantum computers. Therefore, specific applications that require a lot of repetitions to run are typically ill-adapted for these types of hardwares. And this is a metric that a lot of people tend to forget. And this is a metric that is cumulative with the error rates. So if you can carry out much more computations, but the error rates are lower, then overall you have a worse performing machine than if you were to perform less operations, but with much higher fidelity. So there can be some sort of trade-off, but both metrics are important. So both error rates and the frequency and the clock speed are important indicators of how well your quantum computer is adapted to specific tasks. To go back and to give you an idea why a neutral atoms type quantum computer is slower, we have to think back on how an iteration cycle looks like for neutral atoms machine. So as I mentioned, there are three main steps. Catching the atoms, so ensuring that we have enough atoms, positioning the atoms in the computational register, and then carrying out the computation. Out of these three steps, it is the very first step, the catching the atoms, that takes the most time for a neutral atom system. So loading up the register itself is actually the slow part of it. Moving around the atoms is comparatively by orders of magnitude faster, so it can be performed very, very quickly. And the actual computation, so going from the computation register to the end of the computation, is the fastest. So to give you an order of magnitude, the computation cycle, so once you have the atoms where you want them, carrying out the computation takes typically one or a couple of nanoseconds. It can go up to the microsecond scale, depending on the experiment, but the coherence times are quite high, so that typically doesn't pose an issue. Comparatively, loading the register, so the very first step, catching the atoms, can take up to 300 milliseconds. So there is a 5 to 6 order of magnitude difference between the loading and the computational process. So when we say that the neutral atom system's clock speed is low, it actually refers to the fact that the whole iteration cycle is slower because the loading the atoms is currently a main bottleneck for this technology. The actual computation is happening in a comparative gigahertz rate to other types of technologies, but there is this trade-off between having atoms at your disposal in different positions, contrary to the fact that having an integrated circuit, so fixed positions and fixed layout, no matter the computation itself. And finally, there is another important performance indicator that I want to mention, and then I want to have everyone keep in mind, which is the energy consumption. This is a metric, this is an indicator that's rarely being put forward. However, it's being evangelized more and more in recent years, and it is a very important consideration for the technology itself. Certain technologies like neutral atoms or trapped ions, and in specific cases, even spin-based qubits for solid states, have a comparative energy advantage due to the fact that they do not require what we call liquid cryogenics. So they do not require active cooling for the operation itself. Indeed, if you recall, when I presented the architecture of the neutral atom system, at no time we were in need of any really, really low temperature environment for the experiment to be carried out. Why we are talking about cryogenics, especially liquid cryogenics, it is because, as with classical computers, for quantum computers as well, the cooling part is the most energy consuming component of the whole device. So if you are able to manipulate your system or forego the cooling or even reduce the scale of the cooling, then you can save a lot with energy consumption, which can provide a comparative advantage not only with other quantum computing technologies, but with classical computational devices as well. Indeed, CPUs and especially GPUs, even with water cooling, consume a lot of energy to maintain operational temperatures. For a neutral atom system, the operational temperature is maintained by the laser itself. So the energy consumption is concentrated on these laser lights that are very, very energy efficient, especially nowadays with new laser technologies. So this is still a metric that is not considered widely, especially with classical considerations. If you ask a computational center how much energy they consume, they might be able to tell you the overall consumption, but boiling it down for specific computations becomes a much trickier effort. Therefore, highlighting a potential energy advantage for quantum computers is still a long ways off due to the fact that we are missing classical benchmarks in this set. So with that said, again, to recap, what I want you to keep in mind is that when you talk about quantum computers, it's not just about the number of quantum bits, it's also about the error rates, it's also about the repetition rate, and it is also about the energy consumption. Why it is important? It is important because different companies, different initiatives come up with metrics to evaluate how well their system is performing. You might have heard about the quantum volume score that IBM has introduced a couple of years ago. Then they needed to revise it because there were some fundamental problems with them. There are other types of metrics that are being put forward, which typically involve a combination of the number of qubits and the error rates, more specifically. And in more recent years, people are starting to focus on application-based metrics. So application-based metrics can be, for instance, the Q-score introduced by Atos or Eviden, which defines a set of optimization problems and tasks the system to solve these optimization problems in the least amount of time with the best precision possible. And it evaluates the performance based on how well the algorithm can, or how well a solution can be obtained from a specific device. So it doesn't focus on the physical parameters, but it focuses on the applicability. Similarly to that, there was recently a quantum utility score introduced by various players that focus on evaluating the actual impact of a solution instead of raw physical metrics of the system. Both of the approaches, so highlighting physical parameters of a quantum computer or highlighting how well it can perform with applications, are relevant. They can have their own uses, and to give a comprehensive evaluation, both of these metrics or a set of metrics need to be used, especially if one considers what we call benchmarking. So comparing different types of solutions, different types of machines with each other, because at the end of the day, what we are looking for is is deploying these quantum computers for actual computational tasks. So if it needs to have an impact, you need to be able to highlight this impact. With that, I've reached the end of what I wanted to share with you for this initial first session. So let me check if there are any more questions. Since last time, yes, I see a couple more questions, and feel free to leave more questions in the meantime while I'm addressing this. So the first question asks if the quantum computer, intra-atoms quantum computer, needs to prepare the position of the atoms again after we measure the single shot. So the answer is no for the positions. So the laser light itself is calibrated at the beginning of the whole computational cycle, and they can be kept the same throughout the whole computation. However, the atoms need to be liberated and recaptured for a consecutive shot. This is because of the fact that when we do the computation itself, so the computation cycle going from the second element from the computational register to the third element after the computation, you have excited your system. So certain atoms have become excited. These atoms, we are allowed to leave the traps. So you are losing some of your atoms that leave the trap. So they leave the computational space. In order to restart the computation, you need to evacuate the zone and retrap the atoms once again, because not only are you missing atoms to carry out the computation once again, but some of the atoms that are in the vicinity, they become excited. So in some cases, they might even require time to reach back again their fundamental state. This still implies that you can reuse and recycle the atoms themselves. However, you need to retrap the atoms after each shot. And this is also why it takes comparatively more time. Yeah, so the readout itself is almost instantaneous. So it's carried out by the fluorescent imaging. So you're measuring photons emitted by the trapped atoms or the atoms that are still in the traps. And so that's done in, again, on the microsecond level, even faster with certain cameras. For the qubit sizes, there was in the comparative chart, I highlighted 1,600, which is the largest published atomic register, and that was used to base a quantum computer on. So this is the largest published one, and the largest known. To my knowledge, 1,100 is the largest system that can be performed consecutively. From a physical perspective, there are some limitations of how big you can make your quantum register depending on the geometry. So if you put atoms in a single vertical plane, it is around 2,000–3,000 atoms that you will start experiencing some difficulties with handling the register due to the fact that the register size, so the size of the whole space, will reach a mesoscopic regime. So you will start observing non-quantum mechanical effects that will produce additional noise. But from purely a trapping perspective, I think so just to have atoms in specific positions, you can easily scale it up. But the tricky part is you need to be able to compute on these atoms. So you need to ensure that you can evolve quantum information to send quantum information on this whole register. So an additional question on this was about quantum error correction. So quantum error correction, I haven't really touched upon this, is a main means to move forward towards fault-tolerant quantum computing by introducing the concept of a logical qubit instead of a physical qubit. The main idea is that a couple or a set of physical qubits can be used to form a single logical entity, what we call a logical qubit, for more precise computations. So this regrouping is typically done on a very low software level layer. That's why it's called a quantum error correction code. So it is happening on the middleware layer. And depending on the physical type of the machine, different types of quantum error correction codes can be envisioned. For neutral atoms type systems, the most promising ones are surface codes. So the main reference is the publication from hardware that came out last December. So a year ago, by Professor Lukin's team, that introduced neutral atom-specific surface codes for quantum error correction. Nevertheless, it is still an active field of investigation. What type of quantum error correction codes would be the best fit for specific systems? What is clear is that it needs to be tailored to some extent to the physical architecture and the physical parameters of the chosen hardware. So it's not the same quantum error correction code that will work well for superconducting machines than the ones that work well for a neutral atom system, for example. So how quantum circuits work on trapped atoms? We will see an example of that on Wednesday's session, where we will start looking into the implementation side. So I will illustrate how you can create quantum logic gates. But essentially, a quantum logic gate for a neutral atom system is nothing else but a predefined preset laser pulse applied to a single atom. So that's a single qubit logic gate is a specific shape of a laser pulse applied at a specific duration. So you forego some of the parametric freedom in order to apply something specific. But we will see more on that on Wednesday's session. Yes, so memory, or having memory for quantum computing in general is still an active field of investigation. You are correct in saying that we are not really able to store quantum information, at least not in the classical sense. So this is something that's still an unresolved challenge. So there is no such thing as quantum memory. That's why you need to have the readout because the quantum information inherently is very fragile. So this is related to what we call decoherence. So the loss of information over time due to environmental factors, due to the internal instability or many other reasons. So this is called decoherence that's present in all the different systems. Certain types of systems have longer coherence times, so they can keep up the quantum information for a longer period for computation. But at the end of the day, you cannot store infinitely quantum information, so you need to read it out and then repeat the cycle to get a better understanding of what the quantum information was. What you can store, therefore, is the measurements and the observations itself. However, there are recent initiatives on trying to build more efficient infrastructures that are able to prolong the lifetime of quantum information or that are trying to copy quantum information in order to, for instance, interconnect different quantum computers. So the next step of evolution would be how to efficiently connect multiple quantum computers. And for this, an important element is to be able to copy quantum information. So this is still very much academic research topic, how you can perform it efficiently. There are very promising initiatives with atomic systems and especially with photonic systems, which seem to be, for now, the leading section for these kind of investigations. But you are correct in saying that for now, there is no such thing as quantum memory. So a quantum computer in this sense is really a one and done type of machine that it performs the computation, then it's losing the quantum information itself. So for the neutral atom systems, it's not fully connected, so it's not an all-to-all connection. The connection itself is limited to, if I go back to this image, the connection itself is limited to the Rydberg blockade radius. So it's limited to how far you are exciting your outer electron layer, so which orbital you're reaching for the Rydberg state itself in order to carry out the entanglement. So this gives you an interaction radius within which atoms can interact with themselves. So it is one-to-many or many-to-many type interaction, but it's not an all-to-all interaction. Currently, it is only with trapped ion type systems that you can carry out all-to-all interactions. So why digital quantum computing will outperform analog quantum computing? So from a purely theoretical mathematical point of view, it is due to the fact that digital quantum computing is what we call universal quantum computing, meaning that a digital type framework allows you to implement any kind of envisionable quantum algorithm. So analog quantum computers have limitations in a sense that they cannot implement all the different algorithms, at least not very efficiently. There are specific types of algorithms, typically adiabatic evolution that's used for optimization. Most of the quantum simulation experiments and many other algorithms that we will see throughout the next 2 weeks can be efficiently implemented on an analog device, but there are some limitations. The key limitation is quantum Fourier transformation. So quantum Fourier transformation or Fourier transformation in general is an algorithmic tool to transform an discrete entity into a continuous entity or vice versa. So that's the essence of Fourier transformation, to create something discrete out of something continuous or vice versa. Therefore, in a purely analog setup, which is inherently continuous in time, creating something discrete is something that's fundamentally not compatible. I'm not saying you cannot do it. It's just very, very far from the application regime. Therefore, it's very inefficient to implement any kind of quantum Fourier transformation-based methods. And currently, a lot of the algorithms that we know exist from a theoretical point of view build upon quantum Fourier transformation. So in the long run, the main advantage of digital or quantum logic gate-based approaches, or even hybrid, so analog digital approaches, would be the more efficient implementation of quantum Fourier transformation. On top of that, you are correct in assuming that quantum error correction will play a significant role in introducing logical qubits, reducing error rates, because as it stands, analog quantum computing doesn't practically require quantum error correction. It requires what we call error mitigation only. Gauge theory. So that relates to a remark that I made for measurements themselves, that what I introduced is a projection-based measurement or measurement-based quantum computing. But there are other ways to go about. So there are specific types of systems in which you can forego this measurement-based implementation. And in that case, gauge theory can play a significant role. However, that's a very, very niche and very, very experimental approach for now. Are there any reliable sources for hardware research on quantum computer? That's a tricky one because typically hardware researchers focus on their own technologies. The one I know and I use, so I might be a bit biased with this, is the one mentioned here, done by Olivier Ezrati. So on the bottom of the page, Understanding Quantum Technologies is a quantum report and quantum overview that deals in everything from hardware to software and applications. So it's really an all-encompassing report. It's also 1,400 pages long, but it has a quite detailed description on where each of the technologies are. So that could be a good start. Otherwise, it's quite tricky because different hardware providers typically focus on different types of on their own technology only. So we are reaching the end of the time. Let me try to address this last couple of questions quickly. Yeah, so again, for the recommendation, let me just copy in the chat the one I mentioned. That's quite a comprehensive overview. So from Olivier Ezrati, that's just one reference for initial reads, but there are many others. For journals, there is a journal called Quantum Computing that operates, I think, since 2021. There are different articles on it. So you might want to take a look into that. So it's called Quantum Computing, very simply. And if I'm not mistaken, the physical review series A has a specific quantum computing track nowadays as well. So final question about the atom layout and the layout optimization. So the layout is something that we will dive deeper into in other so in upcoming sessions because the atomic layout is part of the algorithmic implementation. For a neutral atom system, where you have your physical qubits, where you have your atoms, is really dependent on the algorithm, on the method you are implementing. Based on certain methods are much more efficient in using a structured square lattice or triangular lattice, while other methods require a more flexible architecture. So it's really dependent on the method you are trying to implement, and therefore the optimization of the layout itself boils down to what kind of algorithm you're implementing. But we will see that with upcoming sessions. With that, I think we've reached the end of the time. Sorry for going 3 minutes over. So thank you very much, everyone, for your attention, for all the questions as well. And if you can join on Wednesday, we will start looking into more on the implementation side, how to work with a specific software tool, how you can start coding for neutral atoms type systems in a very, very high level. So for this session, you won't need any practical programming experience. We will use a no-code environment to look into some quantum computing paradigms and if you can refer to the distributed installation guide for Pulsar Studio to create your account already to access an open access tool. So it's a free tool that we are going to use to work with neutral atom systems on your web browser. So thank you very much again for your attention and hopefully see you around in 2 days.